Have you ever wondered what it would feel like to actually visit the worlds that share our sun with us? Not the distant exoplanets with strange names, but the familiar ones we see in diagrams as simple circles and labels. Up close, they're anything but simple. Some are scorched, some frozen, some wrapped in thick clouds that never clear. Each one has its own kind of day, its own kind of sky, its own story written in rock and ice. Tonight, we're going to move slowly from Mercury outward, staying with the details long enough to picture them in your mind. If you enjoy quiet, careful trips like this, a like, and subscribe helps more space lovers join us. For now, get comfortable. Let's start our journey to the closest planets in our solar system. For many decades, scientists have been watching the universe with patient eyes and better tools. Telescopes on the ground and in space have allowed us to look far beyond our own neighborhood, into regions where we have found thousands of exoplanets and uncounted distant stars. An exoplanet is simply a planet that orbits a star other than our sun, and the sheer number of them tells us that planets are common in the cosmos. Even so, the worlds that orbit our own star are not any less important. They are close enough to study in detail, and they form the reference point for almost everything we think we understand about planets in general. In this journey, we stay inside our own solar system and focus on the objects that lie nearest to us. The path we follow is not through space in a spacecraft, but through knowledge that many missions have gathered over the years. We begin near the sun itself, where space becomes a harsh flow of charged particles, and where the Parker Solar Probe has moved closer to our star than any spacecraft before it. From there, our attention will move outward to the small, sun-baked world of Mercury, then to the thick, cloud-covered atmosphere of Venus, and then on to the dry, ancient landscape of Mars. After leaving the red planet, our view will turn toward the main asteroid belt, where we find rocky bodies of many shapes and sizes. Step by step, we use each stop to build a clearer picture of how our solar system works. Our first stop is the hottest environment in the entire solar system, the region around the Sunday. Together with the data sent back by the Parker Solar Probe, we approach the stormy sea of solar plasma that surrounds our star. Solar plasma is gas so hot that its atoms have been stripped of many of their electrons, and it behaves not only as a fluid but also as a collection of moving electric charges. When we study it up close, we can examine giant prominences that arc away from the sun's surface and bright solar flares that release bursts of energy in a short time. From there, we turn our attention to Mercury, a small planet close to the sun, where parts of the surface reach extreme temperatures, while some regions near the poles remain in shadow and can hold layers of ice that never melt. Farther out, we find Venus, wrapped in a deep, yellowish-white layer of cloud. Under those clouds, the pressure is high, and the air is filled with carbon dioxide and droplets of acid. Lightning flashes through the thick atmosphere, and storms can last for long periods. Beyond Venus, Mars waits with its thin air and cold ground. Its surface carries evidence of a long history. Volcanoes taller than any mountain on Earth, canyons so large that they would stretch across continents on our planet, plains that have been shaped by ancient impacts, and the dry beds of lakes and rivers that no longer flow. Mars attracts special attention because it raises the possibility that simple life might once have existed there, or might still survive in protected places below the surface. After we have considered Mars, we move still farther from the sun to the main belt of asteroids. This region contains many objects that may preserve material from the early days of the solar system, and we study them to look for clues about how planets first formed. The exact details of where such research will lead us are still unknown, but that uncertainty is part of what makes this exploration meaningful. On November 21st, 2021, the Parker Solar Probe reached a distance of about 8.5 million kilometers from the center of the Sunday. Said out loud, that is 8.5 million kilometers, much closer than any space probe had ever flown before. At that distance, the spacecraft passed into the sun's corona, the very hot outer layer that extends outward into space and gradually becomes the solar wind. Because of this, Parker became the first mission that could truly be said to have touched the corona of our star. Reaching that region required engineers to overcome many technical challenges. The heat and radiation near the sun are intense enough to destroy normal equipment, so the probe carries a specially designed heat shield and uses careful flight paths to manage the stress. It is natural to ask why it was necessary to send a probe so close to the sun at all. Moving into an area where almost everything would turn to ash without protection is not something we do lightly. To understand the reason, it helps to take a clear look at what we already know about the sun itself. The sun is a star on what astronomers call the main sequence, the long, stable phase of a star's life when it steadily fuses hydrogen into helium in its core. Its age is about 4.6 billion years, which means it has spent a long time in this steady burning state. In terms of spectral classification, the sun is labeled as type G2V. The G indicates its surface temperature and color. The 2 is a finer subdivision within that group, and the V is a Roman numeral 5 that marks it as a main sequence, or dwarf, star. In everyday language, astronomers sometimes refer to it as a typical yellow dwarf. At the visible surface, or photosphere, the sun has a temperature of about 5,800 Kelvin. When converted to the Celsius scale, this is roughly 5,530 degrees Celsius. Across the surface, there are regions that are somewhat hotter and somewhat cooler. Darker sunspots appear cooler than their surroundings, while bright patches, called faculae, are a bit hotter. If we look deeper inside the sun, or farther out into its outer atmosphere, we find temperatures that reach into the millions of Kelvin. The inner core is extremely hot, and the corona far above the visible surface is also heated to several million Kelvin. However, these very hot regions are thin or hidden from direct view, so they do not contribute much to the bright, white-yellow light that we see with our eyes. In size, the sun is much larger than our planet. Its average diameter is around 1.4 million kilometers, which is about 1.4 million kilometers when read out. This is roughly 109 times the diameter of Earth. If you could line up Earths across the face of the sun, you could set more than 100 Earths in a row from one side to the other. The sun's mass is about 2 times 10 to the power of 30 kilograms, a number that is written as a 2 followed by 30 zeros. Spoken out loud, this is 2 times 10 to the power of 30 kilograms. This mass is roughly 333,000 times the mass of Earth. In fact, the sun contains about 99.9% of all the mass in the entire solar system. The planets, moons, asteroids, and comets together make up only a tiny fraction of the total. We often draw the sun small in diagrams so that the planets can fit on the page, but in reality, it is larger and more luminous than about 80% of the stars in our galaxy that we have been able to study. The sun is also simple in composition when compared to a rocky planet. Most of its volume is made of hydrogen, the lightest element, Hydrogen accounts for about 92% of the sun's total volume. This hydrogen is the main fuel for the nuclear reactions that power the star. In a previous look at how stars evolve, astronomers have shown that, for most stars, hydrogen fusion in the core is the primary energy source during the main sequence stage. Under very high temperature and pressure, hydrogen nuclei, which are single protons, can join together through a series of reactions to form helium nuclei, which contain 2 protons and 2 neutrons. When this happens, a small fraction of the original mass is converted into energy, according to the famous relation E equals mc squared. That is, energy equals mass times the speed of light squared. Over time, helium builds up in the central regions. In today's sun, helium makes up about 7% of its volume and about 25% of its total mass. Along with hydrogen and helium, the sun's material includes small amounts of heavier elements such as carbon, oxygen, nitrogen, and iron. Their combined fraction by mass is small, but these elements still play important roles in how the sun cools and how its interior behaves. Inside, the sun is not uniform. It has a layered structure, with each layer defined by the way energy moves and by the physical conditions present there. At the very center lies the core, a large region where the density and temperature are high enough to sustain thermonuclear fusion. Estimates place the core's diameter at about 25% of the sun's overall diameter. In this central zone, the temperature reaches around 14 million Kelvin. The material is so compressed that a single cubic meter of it would have a mass of about 50 tons. In that environment, hydrogen fusion proceeds continuously. Every second, roughly 4.26 million tons of solar material are converted from mass into energy. This figure, read out, is about 4.26 million tons each second. The energy released there will eventually emerge as the sunlight that warms Earth and the other planets, but the path from the core to the surface is long and slow. Surrounding the core is the region known as the radiation zone. This layer extends outward until about 0.7 times the sun's radius. In the radiation zone, the stellar material is still very dense, too dense for large-scale mixing that could easily carry heat by bulk motion. Instead, energy moves mainly through the absorption and re-emission of photons, the tiny packets of light. A photon created near the core does not travel in a straight line to the surface. Instead, it follows a random walk, being absorbed by an ion in the plasma and then emitted again in a new direction, over and over. Mathematical models show that the temperature in the radiation zone falls from around 7 million Kelvin near its inner boundary to about 2 million Kelvin near its outer edge. Because each photon is scattered, absorbed, and emitted countless times, the overall journey outward is extremely slow. Estimates suggest that a single quantum of light produced in the core may spend anywhere from about 10,000 years to about 170,000 years in the radiation zone before it finally reaches the next major layer. Above the radiation zone lies the convection zone, which forms the outermost part of the sun's interior. Here, the gas is less dense and more responsive to changes in temperature. When material deep in this region is heated, it becomes slightly less dense and begins to rise. As it rises toward the surface, it loses some of its heat and eventually cools enough to sink again. This process sets up large convection cells, somewhat like the rolling motion that appears in boiling water. Although on the sun, the scales are far larger and the physics is more complex. In the convection zone, these cells transport hot plasma from deeper levels up toward the visible surface, while cooler plasma from near the surface sinks downward. Individual convection cells on the surface, called granules, typically remain stable for about 10 to 15 minutes. After that, they break apart and new cells form in their place. This constant movement of conducting plasma, combined with the sun's rotation, acts like a dynamo. It generates and maintains the magnetic field that threads through the sun and extends far into space. This continuous motion of matter creates a magnetic field that pervades the entire inner part of the solar system. The sun is not just a bright disk in the sky. It is also surrounded by an atmosphere made of several layers, each with its own structure and behavior. The lowest of these layers is called the photosphere. This is the region that emits most of the visible light we receive from the sun. So when we look at the sun with proper protection, it is the photosphere that we are seeing as the bright surface. The photosphere is quite thin compared to the size of the sun, with a thickness between about 100 and 400 kilometers. Its temperature is not the same everywhere, but it generally ranges from about 6,600 Kelvin at the hotter parts, which is roughly 6,330 degrees Celsius, down to about 4,400 Kelvin at the cooler parts, or about 4,130 degrees Celsius. These variations help shape features, such as bright regions and sunspots. Above the photosphere lies a more rarefied layer called the chromosphere. This layer is about 2,000 kilometers thick. Under normal conditions, it is hard to see directly from Earth because the photosphere is so bright that it washes out the dimmer light above it. However, during a total solar eclipse, when the moon blocks the photosphere, the chromosphere briefly appears as a thin, colored band around the darkened Sunday. Astronomers can also study it at other times, using special filters and instruments that isolate light from certain atoms. The chromosphere is extremely hot, with temperatures that change from about 4,000 Kelvin near its base to around 20,000 Kelvin higher up. Said another way, that range is from about 4,000 to about 20,000 Kelvin. The outer edge of this layer is marked by spicules, which are narrow, jet-like bursts of hot gas. These jets rise and fall constantly, reaching heights between about 5,000 and 10,000 kilometers above the photosphere. Above the chromosphere lies the corona, the uppermost part of the sun's atmosphere. The corona stretches far into space and includes large structures such as prominences, flares, and extended streams of hot plasma. Some of these features can reach sizes of up to about 1 million kilometers. The gas in the corona is extremely thin compared to the air we breathe, but it is also incredibly hot. Typical temperatures in the corona are around 1 to 2 million Kelvin, and in some regions they can peak at around 20 million Kelvin. This is the environment that the Parker Solar Probe passes through when it dips into the outer atmosphere of the Sunday. Each time the spacecraft goes deeper, it samples plasma and magnetic fields in regions that have never been measured directly before. If we calculate the flow of energy that comes from the photosphere alone, we find that it is not enough to heat the chromosphere and the corona to these very high temperatures. The outer atmosphere is hotter than the layers below it, which is the opposite of what we might expect if heat simply leaked outward. This mismatch is often called a thermal paradox. It tells us that there must be additional physical processes at work in the sun's atmosphere that we do not yet fully understand, processes that deliver extra energy to the upper layers. Several scientific hypotheses have been proposed to explain this. One idea is that magnetic shock waves carry energy upward. In this view, motions in the lower layers of the sun disturb magnetic field lines, sending waves along them. When these waves reach the thinner gas above, they can deposit energy and heat the plasma. Another possibility is that charged particles, such as electrons and ions, are accelerated by the sun's strong magnetic field. As these particles move and interact, they can transfer energy to the surrounding gas and raise its temperature. The Parker Solar Probe was designed specifically to help us investigate these processes and to study what is happening in the upper atmosphere of the sun where these puzzles arise. It is part of a long-term NASA effort to understand the sun and its influence on the space environment around Earth. The mission concept was developed and approved in 2009. 9 years later, on August 12, 2018, the Parker Solar Probe lifted off from our planet on a one-way journey toward the Sunday. Its path, however, was not a simple straight line. To reach the desired orbit, the spacecraft had to perform a series of maneuvers that used the gravity of Venus. Each close pass by, Venus gently changed the probe's speed and direction, allowing it to spiral inward, closer and closer to the central star of our system. Because of the extreme conditions near the sun, the probe had to be designed in a very careful way. A large heat shield, made from special materials, faces the sun and protects the instruments behind it. All the systems on board were built to operate in a harsh environment, with very high temperatures on one side and much colder space on the other. The orbit chosen for Parker keeps it very close to the sun, only for short periods around each closest approach, known as perihelion. After each close pass, the spacecraft moves back out to a somewhat greater distance, where it can radiate away some of the stored heat into space. This pattern helps reduce the overall thermal stress on the probe and gives its systems a better chance to survive multiple orbits. The main goals of the mission are to measure the structure and dynamics of the sun's magnetic fields in its immediate vicinity, to determine how much energy flows outward from the star, to sample particles in the solar wind, and to record wave-like processes in the corona. The solar wind is the constant stream of charged particles that flows outward from the sun and fills the solar system. By studying it up close, Parker can help us understand where it comes from, how it is accelerated, and how it changes with time. These questions are not only interesting for basic science, they also matter for space weather, which can affect satellites, astronauts, and even electrical systems on Earth. As a secondary mission, Parker has also taken images of Venus during its flybys and has observed objects such as Comet Neowise along its path toward the Sunday. To carry out its tasks, the probe is equipped with a wide range of scientific instruments. It carries cameras that can image the solar corona and the surrounding space. It includes instruments that detect and count particles in the solar wind, measuring their energies and directions. Magnetometers on board measure the strength and orientation of the magnetic field. Other sensors track radiation levels and detect radio waves produced by plasma processes in the sun's atmosphere and in the space around it. Together, these instruments provide a detailed picture of the conditions near the Sunday. Many factors make this mission difficult. Besides dealing with critical temperatures near the heat shield, the instruments and electronics are constantly exposed to intense ionizing radiation. Ionizing radiation is high-energy radiation that can knock electrons off atoms and molecules, damaging materials and electronic circuits. The sun also produces strong radio and microwave emissions that create interference around it. This noisy environment makes it challenging to send data back to Earth, because the signals from the spacecraft must compete with the background noise of the sun itself. Engineers have to plan communication windows and data rates carefully to ensure that the valuable measurements are received safely. Despite these challenges, the Parker Solar Probe continues its mission. With each completed loop around the sun, its orbit is adjusted so that the closest approach brings it nearer to the surface than before. Each new perihelion pass carries the probe deeper into the corona, where it can collect fresh data. In the first years of the mission, Parker has already crossed the corona multiple times. The plan calls for the spacecraft to keep tightening its orbit. By about 2024, the distance between the probe and the visible surface of the Sun is expected to shrink to around 6.2 million kilometers. At its closest points, the heat shield may reach temperatures of about 1,370 degrees Celsius, which is roughly 3 times hotter than the daytime surface of Mercury and only slightly below the melting point of iron. Even now, during some of its early close passes, the probe travels at speeds of about 163 kilometers per second at perihelion. Later in the mission, it is expected to reach speeds of about 200 kilometers per second, making it the fastest human-made object ever flown. Because of the extreme environment, the lifetime of the spacecraft is limited. When Parker reaches its closest possible orbit around the Sun, it is expected to complete several revolutions in roughly a year. During that time, it will gradually lose speed as it interacts with the solar environment, and its instruments will face growing stress from heat and radiation. Eventually, the sensitive systems on board will fail. After that, the spacecraft itself will no longer be able to protect its internal parts and will slowly descend into the hotter regions of the Sun's outer layers, where it will be destroyed in the surrounding plasma. Before that final phase, however, the Parker Solar Probe will have transmitted a vast amount of data back to Earth. Those measurements will allow scientists to answer long-standing questions about the Sun and to raise new ones. In this way, the mission will help us take another important step in space exploration, and Parker's flight will certainly not have been wasted. Mercury is one of our closest planetary neighbors in space, but studying it has never been easy. Because it orbits so close to the Sun, we can only see it from Earth, very low on the horizon, and only for a short time just before sunrise or just after sunset. At those times, it is set against a bright sky, and the glare from the Sun makes it difficult to observe in detail. For ancient astronomers, this created real confusion. They sometimes saw Mercury in the evening and sometimes in the morning and thought they were looking at 2 different objects, so they gave it 2 different names. Only when observation tools improved and more careful tracking became possible did it become clear that these 2 stars were the same small planet moving quickly around the Sunday. Modern measurements show that Mercury is the smallest of the 8 planets in the solar system. Its radius is about 2,440 kilometers, which is roughly 38% of Earth's radius. In shape, Mercury is almost perfectly round. The difference between its equatorial diameter, measured across the middle, and its polar diameter, measured from pole to pole, is less than 1 kilometer. For such a modestly sized world, Mercury has a surprisingly large mass. Its mass is about 3 times 10 to the power of 23 kilograms. Spoken out loud, that is 3.33 times 10 to the power of 23 kilograms. This is a little more than half of Earth's mass. If we compare Mercury with bodies of similar size, we find that it is heavier than the moons Ganymede and Titan combined, even though both of those moons have larger diameters. The best explanation for this is that Mercury has an unusually large metallic core made mainly of iron. Inside the planet, scientists think the core of Mercury reaches a radius of roughly 2,000 kilometers. That is about 57% of the planet's total volume. Around this core lies a mantle of silicate rock, which in many models is partly or fully molten. This mantle layer is estimated to be about 400 kilometers thick. On top of the mantle sits a solid crust made of cooled rock with a thickness somewhere between 15 and 37 kilometers. When we look at the surface, we see that it is heavily covered in impact craters of many sizes. The number and condition of these craters, along with the lack of features like active volcanoes and moving plate boundaries, suggests that Mercury has not been strongly geologically active for roughly 3.8 billion years. In other words, its surface has been mostly frozen in place for most of the age of the solar system. For a long time, bright sunlight made detailed observation of Mercury through telescopes very difficult. Until the second half of the 20th century, watching Mercury from Earth was practically the only way to study it, and that gave us only basic information about its orbit and general appearance. This situation changed in 1974 when the Mariner 10 space probe reached the region around Mercury. Mariner 10 flew by the planet and took images that covered about 45% of its surface. It also measured the temperature of the surface and detected that Mercury has a magnetic field, something that was not guaranteed for such a small planet. The instruments on board also discovered that Mercury is surrounded by an extremely thin atmosphere, more accurately called an exosphere, consisting mostly of helium with traces of other gases. 30 years later, on August 3rd, 2004, another mission left Earth, this time named Messenger. Reaching Mercury was not a straight trip. The spacecraft had to follow a complex path using gravity assists from Earth, Venus, and Mercury itself to gradually slow down relative to the Sun and enter orbit. It took several years of precise maneuvering before Messenger could finally settle into orbit around its target. From 2011 to 2015, the spacecraft sent back hundreds of thousands of images, including pictures that together cover almost the entire surface of Mercury. These data allowed scientists to map the planet in detail, to infer more about its internal structure, and to identify features of the landscape that are unique in the solar system. The sensors on Messenger also measured the solar wind and its unusual interaction with Mercury's magnetosphere. The magnetosphere is the region around the planet where its magnetic field interacts with the stream of charged particles coming from the Sunday. Mercury follows an elongated, elliptical orbit around the Sun and completes one full orbit in about 88 Earth days. At its closest approach to the Sun, the point known as perihelion, Mercury lies at about 0.31 astronomical units from the Sunday. An astronomical unit is the average distance between Earth and the Sun, so this means that Mercury is much closer in. At its farthest point, called aphelion, Mercury is about 0.47 astronomical units from the Sunday. Mercury also has a special spin-orbit relationship. Its rotation period, the length of time it takes to turn once around its axis, is about 58.65 Earth days, which is exactly 2/3 of a Mercurian year. That is why we say Mercury is locked in a 3-to-2 spin-orbit resonance. For every 2 orbits around the Sun, the planet rotates 3 times. Because of this pattern, certain longitudes on Mercury face the Sun more often at perihelion and receive more concentrated solar radiation. These regions are called hot meridians. On one of these hot meridians lies the planet's largest impact basin, known as Caloris Planitia. The name can be translated as plain of heat, and it fits well. Temperatures in this region can reach around 700 Kelvin, which is about 427 degrees Celsius, making it the hottest region on the planet's surface. Caloris Planitia is a gigantic impact crater about 1,550 kilometers across. This single structure accounts for roughly 2% of Mercury's total surface area. Estimates suggest that Caloris formed about 3.9 billion years ago, when a large asteroid, likely on the order of 100 kilometers wide, collided with the young Mercury. At that time, Mercury was still a hot protoplanet, meaning a body that had not yet fully cooled or finished forming. The impact would have destroyed much of the newly solidified crust in the target region. Molten lava from below then flooded out over a large area, filling the basin. When this lava cooled and hardened, it created a broad, relatively smooth plain, outlined by a ring of higher terrain. Against the darker surrounding landscape, this ring appears as a bright spot that stands out clearly. The floor of Caloris Planitia itself is sprinkled with many smaller craters, some up to about 100 kilometers in diameter, recording later impacts that struck long after the basin formed. One of the most intriguing features within Caloris Planitia is a system of radial troughs called Pantheon Fossae. This structure is unique in the solar system. It is made up of about 230 linear depressions, or graben-like troughs, that spread out roughly like the spokes of a wheel. The individual troughs are between about 1 and 8 kilometers wide. Most of them are less than about 175 kilometers long, though some extend significantly farther. Near the center of this pattern lies a comparatively large crater called Apollodorus. It is still not clear whether this crater played a direct role in the formation of the troughs, or whether it formed later and just happens to lie near the center. Several hypotheses have been proposed to explain Pantheon Fossae. One idea links the troughs to tectonic activity, suggesting that stress in the crust caused it to crack in a radial pattern. Another idea connects them to the cooling and contraction of the region after the Caloris impact. Caloris Planitia is, in many ways, a land of heat and light. Yet if we move slightly northward on Mercury, we find almost the opposite conditions. Mercury's axis of rotation is tilted by only a very small amount relative to its orbit. As a result, its polar regions never experience strong seasons like those on Earth. Near the poles, the sun always hangs very low in the sky, or never rises at all. The floors of some deep craters near the poles are in permanent shadow and have not received direct sunlight for millions of years. It is no surprise, then, that Borealis Planitia, the plain surrounding the North Pole of Mercury, is the coldest region on the planet. Temperatures in some parts of this area are about 80 Kelvin, which is roughly 193 degrees Celsius below zero. In these permanently shadowed regions, instruments have detected deposits of water ice. The ice may be up to about 2 meters thick in certain places. It is covered by a layer of rocky dust and soil, known as regolith, which helps to shield it from sunlight and reduces evaporation into space. At the same time, not far away, there are highlands and crater rims that do receive direct sunlight. In those sunlit spots, temperatures can climb to about 380 Kelvin, which is around 107 degrees Celsius. This means that on Mercury, areas of extreme cold and significant heat can exist close to each other on the surface. However, Mercury's very thin atmosphere does not transport heat efficiently from one place to another. There is almost no air to carry warmth by winds or convection. Because of this, the strong contrasts in temperature between shadowed and sunlit regions can persist over long periods. Our journey across Mercury's surface now takes us to more southern latitudes, roughly on the same parallel as Caloris Planitia, but about 3,500 kilometers to the west. Here we find one of the planet's other large impact structures, the Rachmaninoff crater. Rachmaninoff has a diameter of about 290 kilometers, and its age is estimated to be roughly 1 billion years. Near its center stands a prominent ring of peaks, called a peak ring, formed by tall mountains arranged in a circle. This central ring is about 130 kilometers across. The rocks within and around the central area have a slightly different color compared with the surrounding plains. They appear more reddish in some images, and the surface shows signs of hardened flows, as if molten material once moved across it. These clues suggest that Rachmaninoff may preserve evidence of relatively recent volcanic activity on Mercury, perhaps among the last large-scale volcanic events on the planet. The lowest point yet identified on Mercury's surface is also located in this region. It lies about 5,380 meters below the planet's average radius. Beyond the central ring, the crater floor transitions into comparatively smooth and dark plains. Continuing farther to the south, we encounter a huge cliff-like structure that stretches for about 820 kilometers from the southwest to the northeast. This feature is called Enterprise Rupes. In some places, its scarp rises several thousand meters above the surrounding terrain. There are many escarpments, or steep slopes, on Mercury, but Enterprise Rupes is the largest known example. Planetary scientists think that such features formed as Mercury cooled over time. As the hot interior slowly lost heat, the entire planet may have shrunk slightly, perhaps losing around 1% of its original volume. When the interior contracted, the solid outer shell, or lithosphere, had to adjust, and it did so by breaking and slipping along faults. These faults push some blocks of crust up over others, creating long, curved scarps that we now see cutting across craters and plains. Nearly half of Enterprise Rupes lies within the basin of Mercury's largest impact crater, Rembrandt. Rembrandt has a diameter of about 716 kilometers. Within this wide basin, the surface is complex and contains many smaller landforms. There are low mountain ridges that run from the outer rim toward the center. These ridges are between about 1 and 10 kilometers wide and can extend up to about 180 kilometers in length. Another ridge system forms a broken ring with a diameter of roughly 450 kilometers inside the basin. On the floor of Rembrandt, we can also see an intricate pattern of deep cracks and troughs that resembles a spider web when viewed from above. This mix of ridges, faults, and fractures suggests a long history of stress and deformation. More detailed study of the rocks and structures in and around Rembrandt is expected to provide clues about Mercury's internal composition and about the processes that have shaped its outer shell. In spite of the careful attention astronomers have given to Mercury and the improvement in observation technology over the decades, the planet remains in many ways mysterious and underexplored compared with bodies like the Moon or Mars. However, this situation is changing. Even now, a new spacecraft named Bepi Colombo is on its way toward Mercury, drawing closer with each orbit around the Sunday. Bepi Colombo is a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency. The instruments on board are designed to gather detailed data on the composition of Mercury's surface and its thin atmosphere, to study the structure of its magnetosphere, and to observe how the solar wind interacts with the planet. The mission will also improve our maps of Mercury's topography, revealing finer details of its hills, plains, and craters. Bepi Colombo has already made flybys of Mercury, passing close to the planet to adjust its speed and trajectory. Still, several carefully planned maneuvers lie ahead. These will use Mercury's gravity and the spacecraft's engines to reduce its speed enough to be captured into orbit. Current plans estimate that Bepi Colombo will enter its operational orbit around Mercury around the middle of this decade, around the year 2025. Once it is in a stable orbit, the spacecraft will begin a long phase of observation, collecting and transmitting new data about this small, dense, and still puzzling world. Venus is the second planet from the Sunday. On average, it orbits at about 0.72 astronomical units from the center of the solar system, which means it is a bit closer to the Sun than Earth is. 1 astronomical unit is the average distance between Earth and the Sunday. Venus needs roughly 225 Earth days to complete one full orbit. Because Earth is also moving around the Sun, the distance between the two planets changes all the time. About every 584 days, the distance between Venus and Earth reaches a minimum, close to about 0.25 astronomical units. At those times, the two planets come as near to each other as their orbits allow. There is an interesting pattern in how Venus faces Earth during these close approaches. Over many cycles, it turns out that nearly the same side of Venus tends to be facing our planet whenever the distance is smallest. This is not a perfect lock, like the Moon's rotation with Earth, but the correlation is strong enough to notice. So far, there is no firm proof that explains why this happens. It might be a subtle effect of tidal forces, the gentle gravitational stretching that Earth and Venus exert on each other over very long timescales. It is also possible that the match is just a coincidence produced by the way their orbital and rotation periods line up. In its basic physical properties, Venus is often called Earth's twin. Its average radius is about 6,052 kilometers, which is about 95% of Earth's radius. Its mass is about 4.87 times 10 to the power of 24 kilograms. Said out loud, that is 4.87 times 10 to the power of 24 kilograms, or about 82% of Earth's mass. The planet rotates very slowly. One full rotation on its axis takes about 243 Earth days. The rotation axis itself is tilted by about 3.4 degrees relative to the plane of the orbit, which is a small tilt compared to Earth's. Venus also rotates in the opposite direction to most planets, a motion called retrograde rotation. But from the surface, that would mainly show up as a very long, strange day-night cycle. For a long time, Venus hid its true surface from observers on Earth behind a thick atmosphere and a permanent layer of bright clouds. In visible light, telescopes could see only this smooth, featureless cloud cover. Because of that, many of the ideas about what lay below were based more on imagination than on data. Some early writers and even a few scientists suggested that Venus might be covered by oceans, perhaps with dense, warm air that could support lush swamps or even a highly advanced civilization. Others thought the surface might be home to exotic life forms adapted to constant cloud and rain. Without direct measurements, these concepts stayed in the realm of speculation. The situation began to change when spaceflight and radio technology advanced enough to probe the planet in other ways. It was discovered that radio waves of certain wavelengths can pass through the clouds of Venus fairly easily, then reflect off the solid surface below. By sending out such radio signals and measuring the echoes, scientists can build up a kind of radar image of the terrain, even though it is hidden from view by clouds. This technique made it possible to create the first global maps of Venus's surface. In 1978, the American spacecraft Pioneer Venus 1 entered orbit and used radar to map large parts of the planet. Soviet orbiters also collected important data around the same time. Early maps, however, had a fairly low resolution. Features smaller than about 1 to 2 kilometers often could not be seen clearly, and only the largest mountains and basins stood out. To move beyond these limits, a more specialized mission was needed. This led to the launch of the Magellan orbiter, which carried a powerful radar system designed specifically to study Venus. Between 1990 and 1994, Magellan sent back radar images that covered about 95% of the planet's surface. The resolution in many areas reached about 120 meters. That level of detail let researchers identify individual flows of lava, fault lines, and many smaller impact craters. Even today, the information collected by Magellan is considered the most complete and accurate dataset we have for the surface of Venus. Before talking about the surface of a planet, it is helpful to have at least a general idea of what lies inside. According to the most widely used models, Venus has a metallic core at its center, made mainly of iron and nickel. The mass of this core is thought to account for about 25% of the planet's total mass. Unlike Earth, Venus does not show signs of a global magnetic field today. That absence suggests that, if the core is metallic, it is likely in a state where large-scale motion is limited, perhaps more solid than liquid in key regions. Around the core lies a thick silicate mantle, which extends outward for up to about 3,000 kilometers. Above the mantle is a solid crust with an average thickness of about 16 kilometers. On Earth, the outer shell is broken into tectonic plates that move relative to each other. On Venus, the lithosphere, which includes the crust and the uppermost mantle, does not seem to form such distinct plates. High temperatures inside the planet and the high viscosity of the rocks probably keep the lithosphere from breaking into many separate, rigid blocks. This means that Venus's geological activity works differently from Earth's. Instead of long, narrow plate boundaries and wide oceans, Venus displays broad regions where the crust has been stretched, compressed, or broken on a more local scale. One striking property of Venus's surface is that it does not show as many large impact craters as one might expect on such an old planet. Large areas are covered by vast plains of solidified lava called volcanic plains. These plains suggest that, in the past, molten rock flowed out over huge regions, resurfacing much of the planet and erasing many older craters. In addition to familiar landforms like mountains, ridges, and basins, Venus also hosts some terrain types that are not found on other planets. One example is tessera terrain. Tesserae are highly deformed, mountainous areas where ridges and valleys intersect in a complex pattern that can look, in radar images, a little like overlapping roof tiles. Other distinctive landforms include structures known as arachnoids and coronae. These are roughly circular or oval features, often a few hundred kilometers across. At first glance, they may look like impact craters, but their internal structure and surrounding faults show that they formed through tectonic and volcanic processes, not from incoming objects. Because radar images of Venus are not as intuitive as photographs, an untrained viewer might not notice much detail at first glance. To bring out the topography more clearly, scientists often use elevation maps, where different heights above or below a reference level are shown in contrasting colors. On such a map, the region that immediately stands out is the largest highland area on Venus, known as Aphrodite Terra. Regions like this can be thought of as the rough equivalents of continents on Earth, although Venus has no oceans of liquid water. Aphrodite Terra is a huge territory that stretches along the equator. Its mountainous terrain is complex, with ridges and plateaus arranged in several large blocks. Depending on exactly how its boundaries are drawn, Aphrodite Terra may be as long as about 18,000 kilometers and as wide as about 5,000 kilometers. This gives it an area between about 29 and 41 million square kilometers, which is comparable to the area of Africa on Earth. Within Aphrodite Terra, three broad regions are especially noticeable: Atla Regio, Thetis Regio, and Dione Regio. Atla Regio lies in the eastern part of this highland and contains some of Venus's most impressive volcanoes. The highest of these is called Maat Mons. The distance from the base of Maat Mons to its summit is about 5 kilometers, measured from the average level of Venus's surface. The total height of the volcano is estimated to be between about 8.3 and 8.8 kilometers, depending on the method of measurement. That makes it one of the tallest known volcanoes on the planet. At present, Maat Mons appears to be dormant. However, several lines of evidence suggest that it may have erupted in geologically recent times. Radar images show relatively fresh-looking lava flows on its slopes, and the small number of impact craters in those areas indicates that the surface there is not very old. Farther west within Aphrodite Terra lies another region of interest, where the patterns of ridges and fractures reveal intense tectonic activity. In places, the mountain chains run in different directions, crossing each other and forming a mesh of highlands. This suggests that the crust here has been pulled and squeezed by forces acting from several directions at once. Deep fractures cut across the terrain, and some of these long cracks show signs that lava once rose through them and spilled out onto the surface. These features may represent some of the most unusual volcanic systems on Venus, where tectonic stress and magma movement are closely linked. Moving farther toward the western edge of the highland, we come to the area where several Venera probes from the Soviet Union were aimed. 4 landers were targeted at Venus in this general region. 2 of them survived the intense passage through the atmosphere and reached the surface, while 2 others were destroyed before landing. The planned landing sites and impact areas lie in the southern part of a huge lowland region called Guinevere Planitia. This plain extends for many thousands of kilometers and rivals Aphrodite Terra in area, although it lies lower in elevation. Despite being called a plain, Guinevere Planitia has a complicated relief. It shows a mix of different geological formations rather than a single flat floor. According to current interpretations, the crust in this region was compressed for hundreds of millions of years by tectonic forces. This long-lasting pressure folded and crumpled the rocks, creating ridges and wrinkle-like features. At the same time, lava rose through cracks and fissures and flowed out over the surface, filling the lower areas. As the lava cooled, it formed smooth volcanic plains that now occupy many of the low spots. The end result is a landscape that combines broad, relatively flat areas with clearly defined uplands and faulted ridges. From orbit, this patchwork of plains and highlands points to a history in which both tectonic deformation and volcanic flooding played major roles. The western part of Guinevere Planitia borders an elevated region known as Beta Regio. In radar images, Beta Regio appears relatively bright, which means it was one of the first features of Venus's relief to be noticed and named. It is an uplifted area that is roughly circular, with a diameter of around 2,000 kilometers. This region is also known as the final resting place of the hardware from the Venera 9 and Venera 10 missions. These spacecraft returned the first close-up images of the surface of Venus in 1975. They also measured key properties of the atmosphere, such as pressure and temperature, and sampled the composition of the surface material. The rocks at their landing sites turned out to be similar in composition to basaltic rocks on Earth, which are common volcanic rocks. Putting these pieces together, scientists have concluded that Beta Regio is probably one of the largest volcanic massifs on Venus. Its combination of raised topography, radial and concentric fractures, and evidence of past lava flows all support this view. Because of these features, Beta Regio is considered one of the most promising places on the planet to search for signs of ongoing or very recent volcanic activity. In other words, if there are active volcanoes on Venus today, this area offers some of the highest chances to discover them. Moving north on Venus, we come to the second largest highland region, a kind of conditional continent called Ishtar Terra. In broad terms, it stretches about 8,000 kilometers from east to west and roughly 2,200 kilometers from north to south. Its total area is about 8.5 million square kilometers, making Ishtar Terra only slightly larger than Australia on Earth. Near its center rises the biggest volcanic massif on Venus, known as Maxwell Montes. These mountains stand about 11 kilometers above the planet's average surface level and about 7 kilometers above much of the surrounding terrain. Around the highest central peak lies a relatively flat plateau, about 200 kilometers by 400 kilometers in size. Across this plateau, the difference in elevation is no more than about 1.5 kilometers, so individual peaks are hard to separate clearly with current measurements. Maxwell Montes is not only tall, it is also one of the coldest areas on Venus. While cold is a relative term here, the temperature at these heights is estimated to be around 380 degrees Celsius, significantly lower than the temperatures in the lowlands. The air is thinner there as well. The atmospheric density over the peaks is thought to be about half of what it is at the planet's mean radius. Yet even in this thinner region, the atmosphere is still more than 40 times denser than Earth's at sea level. In radar images, Maxwell Montes appears unusually bright. This suggests that the surface of the peaks and slopes is coated with materials that reflect radio waves especially well. One idea is that metallic compounds, perhaps containing sulfur, such as pyrite, hematite, or galena, may play a role. At the high temperatures of the lowlands, these substances could evaporate from rocks and then rise with the atmosphere. When the gas reaches cooler mountain regions, the compounds may condense and settle out as a fine-grained coating, somewhat like a metallic frost on the slopes. Looking over the surface of Venus, it is natural to wonder whether humans will ever be able to explore these places directly. The idea of walking among the mountains of Maxwell Montes or standing on the lava plains of Guinevere Planitia is appealing, but the environment is extremely hostile. The atmospheric pressure at the surface of Venus is about 93 times higher than the pressure at Earth's sea level. The average temperature near the ground is around 737 Kelvin, which is roughly 464 degrees Celsius. At such temperatures, lead would melt, and most ordinary metals and electronics would fail quickly. Even robotic landers that are specially designed to withstand harsh conditions usually survive on the surface for only about an hour before their systems overheat and fail. Because of this, the notion of terraforming Venus, changing the entire planet to make it more Earth-like, seems far beyond our reach with any technology we can realistically expect soon. On the other hand, the atmosphere of Venus is not uniform from top to bottom. There are layers high above the surface where the temperature and pressure are much closer to those on Earth. In those middle levels of the atmosphere, the pressure is roughly similar to one atmosphere, and the temperatures fall into a range where liquid water could potentially exist if it were present. During the last century, some researchers suggested placing long-term stations or even large habitable structures in those layers. These ideas involved floating platforms or aerostats filled with lighter gases, which would allow habitats to hover in the sky well above the crushing pressure and extreme heat at the surface. In theory, such bases could study the planet and its atmosphere more safely. In practice, however, building and supporting such floating cities would be a major engineering challenge. The chemical makeup of the atmosphere, dominated by carbon dioxide and clouds of sulfuric acid, also complicates matters. For now, these concepts remain proposals, and the real possibility of carrying them out is still an open question. Whether or not people ever live in the skies of Venus, the planet can be studied in detail by orbiters and probes, and its complex geology and climate will continue to be a subject of investigation. Turning our attention outward, we come to Mars, the next planet beyond Earth. Mars orbits the Sun at a distance of about 1.5 times Earth's orbital distance. Its radius is roughly half that of Earth, and its mass is about 10.7% of Earth's mass. Because it is smaller and lighter, the surface gravity on Mars is weaker, only about 1/3 of what we experience on Earth. A person who weighs 70 kilograms on Earth would feel as if they weighed only a little more than 20 kilograms on Mars. The temperatures on Mars are lower than on Earth and vary strongly with location and season. At the poles, winter temperatures can drop to around 100 degrees Celsius below zero, and even in less extreme conditions, they can remain more than 50 degrees Celsius below zero. Near the equator, on a warm afternoon, temperatures can sometimes rise to about 35 degrees Celsius above zero, but the air is so thin that heat escapes quickly once the sun sets. The total area of Mars's surface is roughly the same as the combined area of all the continents on Earth. This gives us a useful mental picture. If Mars were divided into oceans and continents in a similar way to Earth, then all the land you know on our planet would just about fit onto Mars's surface. The landscape is extremely varied. Some regions resemble familiar terrestrial features, such as volcanoes, canyons, and river valleys, while others are unlike anything on Earth. Today, 8 automatic spacecraft orbit Mars and monitor the planet closely. Their cameras and instruments have mapped the surface in great detail and have allowed us to pick out key landmarks. One of the most striking is a bright region in the Western Hemisphere that corresponds to the largest volcano in the solar system, Olympus Mons. This is where we begin a closer tour of the red planet's surface. Olympus Mons rises about 26 kilometers above the surrounding plains. That is roughly 2.5 times the height of Mount Everest, measured from sea level on Earth. Its structure is that of a shield volcano, a broad, gently sloping mountain built up over time by repeated outflows of lava. Current models of Mars's interior suggest that the planet does not have active tectonic plates sliding past or under one another as Earth does. Without moving plates, a volcanic hotspot can remain under essentially the same location for hundreds of millions or even billions of years. Lava erupting from this fixed source spreads out over large areas, layer by layer, and eventually forms a wide volcanic shield. For Olympus Mons, the average diameter is about 600 kilometers, and the total area of the volcano is more than 300,000 square kilometers. That area is similar to that of a medium-sized European country such as Poland or Italy. At the summit of Olympus Mons lies a large central depression made up of several overlapping calderas, which are collapsed volcanic craters formed after major eruptions. The depression is about 85 kilometers in diameter and reaches depths of up to 3 kilometers below the surrounding summit plateau. Because the volcano is so high, the atmospheric pressure at the top is much lower than at the base. Measurements indicate that the pressure at the summit can be about 50 times lower than at the foot of the mountain. Since the Martian atmosphere as a whole is about 160 times thinner than Earth's at sea level, conditions at the top of Olympus Mons are close to a near vacuum compared with what we are used to. Parachutes that work in thicker air would not generate enough drag there, making it very difficult to land a probe or rover directly on the summit. The slopes of Olympus Mons are, on average, quite gentle, with grades around 5%. That means a rise of 5 meters for every 100 meters traveled horizontally. However, near the edges, the the volcano drops off in steep escarpments that can be up to 7 kilometers high. The exact origin of these dramatic cliffs is still under debate. Some hypotheses suggest that long-vanished oceans or large bodies of water may have eroded the base of the volcano in the distant past. Others point to the role of giant landslides or repeated dust storms that steadily removed material from the margins. When we conceptually descend from Olympus Mons and move across the terrain around it, we see many overlapping ridges and isolated hills. Some of these structures extend as far as 1,000 kilometers from the volcano's edge. They may have formed as the slopes of Olympus Mons slowly failed and slumped outward, or they may include deposits left by ancient ice sheets that once flowed around the mountain. Traveling southeast from Olympus Mons, we encounter a vast volcanic plateau known as the Tharsis region. This elevated area, built largely from solidified lava flows, covers roughly 1/4 of the planet's surface. Its area, around 30 million square kilometers, is comparable to the size of the African continent. The Tharsis rise stands about 10 kilometers higher than the surrounding plains. Its age is estimated at about 3.7 billion years, indicating that large-scale volcanic activity there began early in Mars's history and continued for a long time. Within Tharsis, there are many large volcanoes, some of them only slightly smaller than Olympus Mons. One prominent example is Arsium Mons, which reaches a height of about 19 kilometers. That makes it the second highest peak on Mars. The summit of Arsium Mons is marked by a large caldera, about 110 kilometers across, and the base of the volcano spreads out over more than 400 kilometers. Each Mars year, for a short period, a special cloud formation can be seen over this volcano. As sunlight warms the mountain's slopes, small dust particles are lifted by rising air currents. These particles and water ice crystals can combine to form a dense, elongated cloud that stretches downwind from the summit. This cloud can reach altitudes of up to about 30 kilometers above Arsium Mons and can be carried across great distances by the winds. It is a reminder that even in Mars's thin atmosphere, complex weather patterns can appear around large topographic features scattered across the Tharsis region. We also find vertical pits, dark openings that drop steeply into the subsurface. Their bottoms are not visible in most images, suggesting considerable depth. The largest of these pits are about 150 meters in diameter, and their depths are estimated to be at least 178 meters. Many researchers interpret them as skylights into collapsed lava tubes. Lava tubes form when the surface of a flowing lava stream cools and hardens, while hot lava continues to move inside. When the internal flow eventually stops and drains away, a hollow tunnel can be left behind. If part of the roof later collapses, a pit forms that opens into the tube. Such structures are of interest not only for geology, but also as potential natural shelters for future robotic or human explorers, since they could offer some protection from radiation and temperature swings. Over billions of years, the dozens of overlapping shield volcanoes in Tharsis released enormous amounts of gases into the Martian atmosphere. During their eruptions, they would have emitted large quantities of carbon dioxide and water vapor. Mathematical models suggest that the total amount of gas released could have been sufficient to create an atmosphere 1.5 times as dense as Earth's current atmosphere at sea level. Conditions under such an atmosphere, combined with a warmer young sun and additional greenhouse effects, might have been far more favorable for liquid water on the surface, and perhaps for the origin and persistence of life. However, Mars has a comparatively weak gravitational field because of its small mass. Over long periods, it was not able to hold on to a thick atmosphere. Interactions with the solar wind, the loss of its global magnetic field, and gradual escape of light gases to space all contributed to thinning the air. In the end, Mars failed to retain its atmosphere and was eventually stripped of it. Traveling east from the Great Volcanic Plateau, we arrive at one of the most dramatic features on Mars, the region known as Valles Marineris. It is a network of enormous canyons that stretches almost across a quarter of the planet's circumference. The system is about 4,500 kilometers long, up to about 600 kilometers wide, and in places more than 11 kilometers deep. For comparison, its length is greater than the distance from one side of North America to the other. When we look at detailed images, we see that the slopes of many canyons in the central and western parts of Valles Marineris are layered. The walls show clear bands of rock stacked on top of one another, a pattern typical of sediment deposited on the floor of a large body of water. This observation has led many scientists to think that, in the distant past, at least some sections of these canyons may have been filled or partly filled with water. If water once stood in these deep valleys, the sediments at their bottoms could hold a record of past environments over long spans of time. In principle, they might preserve the chemical signatures of ancient lakes, and if life ever existed there, they could even contain microscopic fossils or other traces. For now, those layers are far beyond the reach of direct sampling, but they remain high on the list of places that future missions could target when we are able to explore more deeply. The eastern parts of Valles Marineris look different from the main troughs. There, the relief is more chaotic. Instead of one main canyon, we find a maze of smaller, intersecting valleys, broken mesas, isolated hills, and low plateaus. This kind of topography is often called chaotic terrain, and it may mark areas where large volumes of subsurface ice or water once melted or drained away, causing the ground above to collapse. Farther to the north, the rugged terrain gives way to a smoother region known as Chryse Planitia. This is a broad plain where the surface appears comparatively even on large scales, although smaller craters and ridges are still present. Chryse Planitia is notable in the history of Mars exploration as the landing area for some of our earliest robotic visitors. It is here that the Sojourner rover, delivered by the Mars Pathfinder mission, explored the surface in the late 1990s. It is also in this general region that the Viking 1 lander touched down in 1976, sending the first color images of Martian landscapes back to Earth. Those early pictures of rocks, sand, and a dusty pink sky changed Mars from a remote point of light into a place with a visible horizon and a real surface. According to widely accepted ideas today, Valles Marineris began to form early in Mars's history, when the planet's crust was still adjusting to forces from below. Later, erosion processes, such as landslides, wind action, and possibly flowing water deepened and widened the canyons. One hypothesis connects the origin of this canyon system with the volcanic activity in the Tharsis region to the west. In this view, the immense weight of the Tharsis volcanic plateau and the rising of hot material in the mantle beneath it stretched the crust, causing it to fracture and open up into a system of large troughs, or chasmata. Another hypothesis points to a link, at least in terms of overall stress patterns, with Utopia Planitia on the opposite side of the planet. In both cases, the key idea is that deep internal and surface forces together tore the crust along great faults and created a canyon system unlike anything on Earth. Utopia Planitia itself is a huge, roughly circular lowland in the northern hemisphere of Mars. It is generally interpreted as the scar of a gigantic impact, a basin left behind after an extremely large asteroid struck the planet long ago. The basin's diameter is about 3,300 kilometers. The terrain across much of Utopia Planitia is relatively flat and smooth, interrupted mainly by small craters and gentle rises. Several missions have been sent to study this region from orbit and from the ground. In 1979, the Viking 2 lander transmitted panoramic images of its surroundings, showing a stony, dust-covered plain. More than 3 decades later, in 2016, the SHARAD radar instrument on the Mars Reconnaissance Orbiter detected large deposits of water ice mixed with dust beneath the surface in parts of Utopia Planitia. The radar measurements indicated that this ice-rich layer lies at depths between about 1 meter and 10 meters. In May 2021, the Chinese rover Zhurong landed successfully in Utopia Planitia. Since then, it has traveled more than 1,000 meters across the surface, returning hundreds of images and scientific measurements. Zhurong carries instruments to study the local geology and the structure of the shallow subsurface. However, it cannot dig deeply enough to reach the buried water ice layer directly, because that layer lies several meters below the ground. Even so, the rover's observations help refine our understanding of how ice and dust are distributed near the surface and how Utopia Planitia has evolved over time. To the north, Utopia Planitia merges into Vastitas Borealis, a vast lowland that surrounds much of the planet's northern region. Vastitas Borealis covers about 40% of the Martian surface, making it one of the largest continuous geographic units on the planet. Some scientists have proposed that this northern lowland could once have held an ocean, or at least large seas, when Mars had a thicker atmosphere and warmer climate. If that is true, Utopia, Planitia, and nearby regions might preserve shorelines or other features shaped by standing bodies of water. This idea is still being tested, and new data from orbiters and landers continue to refine the picture. Moving southwest from the center of Utopia Planitia, we come to another important plane, Isidis Planitia, which forms part of the rim of a large impact basin. On the western edge of Isidis Planitia lies a feature that has received special attention in recent years, Jezero Crater. Geological evidence indicates that millions or billions of years ago, there was a lake inside this crater. Over time, the lake dried out, leaving behind sediments and landforms that record its history. On February 18th, 2021, the Perseverance rover from NASA landed inside Jezero Crater, accompanied by Ingenuity, the first helicopter ever flown on another world. Since then, the rover and helicopter have been exploring the crater floor and the remains of an ancient river delta that once flowed into the lake. Jezero Crater is estimated to have formed about 4 billion years ago when a large celestial body struck the Martian surface. The crater is about 49 kilometers across. The choice of this site for the Perseverance mission was not accidental. Jezero was selected because it appears to be one of the most promising places on Mars to search for signs of past life. The inlet channels and delta deposits show that water flowed here for a significant period. The time when this likely happened falls within what scientists call the Hesperian period of Martian geological history. The Hesperian is thought to have begun around 3.5 billion years ago, and to have lasted for roughly 1 billion years. During at least part of that era, the atmospheric pressure on Mars may have been comparable to the pressure at Earth's surface, and the average surface temperature may have reached around 50 degrees Celsius. Under such conditions, liquid water could have been stable on the surface in many places. Rock samples recently drilled from the floor of Jezero Crater by Perseverance provide strong support for the idea that this environment was shaped by water. Analyses performed with onboard instruments show that the rocks have been altered by long-term contact with liquid water. Their minerals and textures record repeated cycles of wetting and drying, or of interaction with groundwater. These samples are being stored in carefully sealed tubes, with the goal of returning them to Earth in a future mission for more detailed study in laboratories. Even with the instruments it carries now, Perseverance has already delivered a wealth of data and images that are reshaping our view of Mars's past. The rover was designed for many years of operation, on the order of about 14 years under favorable conditions. That long design lifetime means that if systems remain healthy, Perseverance will be able to explore a large portion of Jezero Crater and possibly move beyond it, collecting cores from a wide range of rock units. There are still many samples to drill and many kilometers of Martian terrain to cross. Each new layer of rock and each new outcrop can add another piece to the story of how Mars changed from a wetter, possibly more habitable world to the cold, dry planet we see today. For that reason, the survey of Martian landscapes is still very much in progress, and the exploration of this planet is far from finished. In many reconstructions, Mars, several billion years ago, would not have looked like the cold, dry world we see today. Instead, models suggest a planet wrapped in a thicker atmosphere rich in carbon dioxide, with heat and moisture held close to the surface. Under that heavier blanket of air, liquid water could exist more easily. Rivers flowed across the lowlands, carving channels and valleys, and large parts of the northern hemisphere may have been covered by standing water, perhaps in the form of broad seas or a single large ocean. Over time, though, all of this changed. The surface water gradually disappeared, leaving only signs preserved in rocks and landscapes. A major part of this change is linked to the planet's magnetic field. Mars appears to have had a global magnetic field early in its history, but that field was weak and unstable compared with Earth's. A strong magnetic field can deflect much of the charged particle stream, known as the solar wind. Without that protection, the upper layers of a planet's atmosphere are directly exposed to the constant flow of energetic particles from the sunday. Over hundreds of millions of years, the solar wind stripped away gas from Mars's atmosphere. At the same time, ultraviolet light from the sun split water vapor in the upper atmosphere into hydrogen and oxygen. Hydrogen, being light, rose higher and eventually escaped into space. Much of the oxygen left behind reacted with iron-bearing minerals in the rocks and dust, forming iron oxides. This slow process gave Mars its overall reddish color, the tint of rust, and left behind a thin atmosphere and a surface coated in an orange layer of dust over ground that is largely frozen. To better understand what is happening on Mars today, it is helpful to look beneath the surface. Seismometers carried by the InSight lander, which has been listening to Marsquakes for several years, have provided important clues about the planet's internal structure. At the center of Mars lies a large, dense core made mainly of iron with additional sulfur and nickel. The radius of this core is more than half the radius of the entire planet. Its temperature is estimated to lie between about 1,800 and about 2,000 Kelvin. Under the enormous pressure at those depths, most of the core is thought to be in a solid or partially solid state. Because a stable global magnetic field is usually generated by the motion of liquid metal in a core, a mostly solid core helps explain why Mars no longer has a strong protective magnetic field. Surrounding the core is the mantle, a thick shell of rock that is hot but mostly solid on human timescales, with regions that may be partially molten. The Martian mantle is about 1,200 kilometers thick. Its composition changes with depth, deeper layers are enriched in various metal oxides, while the upper mantle is made mostly of minerals such as olivine and other silicates, similar to those found in Earth's upper mantle. On the outside, the mantle is capped by a massive crust. The average thickness of this crust is estimated to be around 50 kilometers. That is 5 to 10 times greater than the thickness of Earth's oceanic lithosphere and is comparable to the thickness of Earth's continental crust. There is also a contrast between the two hemispheres. In the northern hemisphere, the crust is dominated by rocks with compositions similar to andesite, while in the southern hemisphere, basaltic rocks are more common. This difference suggests that the crust in the two hemispheres may have formed at different times or through different processes. Decades of orbital observation have yielded hundreds of thousands of high-resolution images of Mars. By combining these images with topographic data, scientists have created extremely detailed maps of the planet. These maps include many features: small craters, only a few meters across, long valleys and ridges, and vast structures that stretch thousands of kilometers and can be seen even with large telescopes from Earth. One of the most impressive of these large-scale features is, again, Valles Marineris. This giant system of interconnected canyons and chasms runs along the equator for about 4,500 kilometers. Its western end is closely linked with the immense volcanic rise of the Tharsis Plateau. If we imagine descending into this region, our path might begin near the central part of the plateau at a unique and complex area known as Noctis Labyrinthus, the Labyrinth of Night. Noctis Labyrinthus covers a zone about 1,200 kilometers across from west to east. It is characterized by chaotic terrain, numerous deep, steep-walled troughs intersect and cross each other, breaking the surface into irregular blocks and mesas. The upper parts of these blocks consist of softer, lighter-colored sediments that have been heavily eroded. Beneath them lies more solid bedrock. Over billions of years, the walls and edges of the troughs have collapsed in many places, leaving behind landslides and debris fans that now partly cover the original slopes. Geological evidence points to the role of water in shaping this terrain. It is thought that, in the distant past, rain or snow that fell on higher regions of the Tharsis Rise accumulated here and flowed eastward through the fractures, forming powerful streams. The floors of many chasms show deep erosion patterns typical of water flowing at high speed. The layered structure of some slopes and of the landslide deposits at their bases also suggests that sediments were laid down in repeated cycles, possibly in standing or slowly moving water. Spectral analysis of the surface material shows that certain minerals are abundant in this region, minerals that typically require liquid water to form. Examples include hematite, some forms of opal, and various sulfate minerals. Their presence supports the idea that water was once active in and around Noctis Labyrinthus. Modern observations reveal that Noctis Labyrinthus is also one of the more humid regions on Mars today, even under present cold and dry conditions. Images and weather data show that dense fog sometimes collects in the troughs and hollows. One explanation is that water in the soil slowly evaporates during the warmer part of the day, adding moisture to the thin Martian atmosphere near the surface. The high walls of the gorges help trap this moist air, preventing it from mixing easily with the drier air above the plateaus. As temperatures drop at night, the water vapor condenses into microscopic ice crystals. These crystals settle to the ground as a light frost, forming a thin, temporary coating on the rocks and dust. The cycle then repeats, with frost sublimating back into vapor as the sun rises. Moving eastward from Noctis Labyrinthus, the tangled network of short troughs gradually transitions into the broader main canyons of Valles Marineris. Over immense spans of time, large streams of water, active when the climate was warmer and the atmosphere thicker, cut deep channels into the Martian bedrock. Later, as the surface dried and cooled, winds and sandstorms became the dominant agents of change, gradually wearing away at the canyon walls and transporting fine particles along the valleys. Regardless of the exact path one might imagine following through the labyrinth of chasms, eventually, the routes lead into one of the major troughs, often identified as Coppertie's Chasma in this context. It is here that the deepest point in Valles Marineris has been recorded, lying about 11 kilometers below the level of the surrounding plateau. Calculations and geological reconstructions suggest that, in ancient times, this deep section may have held a long, narrow lake. At its fullest extent, the volume of water in this lake could have been comparable to the volume of the Earth's Black Sea. That makes it an especially interesting target for future exploration. The sediments on the canyon floor may preserve traces of past microorganisms, if any ever lived there. The canyon walls, with their stacked layers, are like pages in a book, recording the geological history of Mars over long intervals. Reading that record in detail would teach us much about the planet's changing climate and internal activity. As we follow the canyon system farther downstream, we find that its walls become less steep, and the Great Rift slowly opens out into the broad lowlands of Christ Planitia. Even here, far from the deepest chasms, we can still see the marks left by water. Rounded terraces, streamlined hills, and elongated islands appear in the landscape. Features that likely formed as sediments from Valles Marineris were eroded, transported, and deposited. Similar types of landforms can be found in the deltas and floodplains of major rivers on Earth, such as the Amazon and the Nile. Together, these features make Valles Marineris and its outflow regions some of the clearest and most striking evidence that liquid water once shaped large parts of the Martian surface. Despite this, the giant rift of Valles Marineris has so far only been explored from above. Orbiters have mapped it in impressive detail, but no rover has yet driven down its slopes or across its floor. The wheels of a Mars rover have never touched the interior of these canyons, leaving them as one of the most dramatic yet still unvisited landscapes in the solar system. To get a closer look at the red planet, we travel far to the east. After crossing several thousand kilometers of harsh, rocky desert in our mental map, we arrive at a broad impact structure known as Gale Crater. About 3.8 billion years ago, a large asteroid struck this region with tremendous energy, carving out a circular depression about 154 kilometers across. In the middle of this crater stands Mount Sharp, also called Aeolus Mons, a vast, irregular central uplift built from many layers of sedimentary rock. These layers rise kilometer above kilometer, stacked like a slow record of changing conditions. In earlier times, scientists think that Gale may have held a deep, round lake with a central island that later became the core of Mount Sharp. Today, the crater is dry, but the rocks inside it still preserve traces of that watery history. Gale Crater is now best known as the landing site of the Curiosity rover. The story of this rover began in early August of 2012, when the spacecraft carrying it descended through the Martian atmosphere and set it down safely on the surface on August 6th. Curiosity was designed as an autonomous mobile laboratory, a symbol of patient, systematic exploration. Its main goals were to study the local climate and geology, to look for evidence of past water and to assess whether the environment had ever been able to support microbial life. Almost immediately after landing, Curiosity sent back images that showed clear signs of a wetter past. One of the first areas studied near the landing site contained rounded pebbles cemented together in a way typical of an ancient stream bed. The shapes and sizes of the stones suggested that they had been carried and tumbled by flowing water. The channel feeding this area has been named Peace Vallis, or Valley of Peace, and it stands as one of the clearest examples of water erosion near the rover's path. Such features indicate that, long ago, water once flowed here at the surface with enough force and duration to move gravel and sand. After its first surveys, Curiosity drove eastward and soon reached a small area of wind-blown sand, nicknamed Rock Nest. There, the rover used its scoop to collect the first soil sample for detailed analysis. Instruments heated the sample and measured the gases released. The results showed that the soil contained about 3% water by weight. This does not mean there are liquid pools in the ground. Instead, tiny grains of dust and minerals hold water molecules bound within their structure. Even so, the finding confirmed that water is present in the near-surface materials, and that under the right conditions it could be released. From Rocknest, the rover turned to the southwest and continued its slow journey. It crossed the rocky flats of an area named Glenelg, where wind had stripped away loose material and exposed hardened layers of bedrock. Some of these rocks formed more than 4 billion years ago, when Mars was very young. By analyzing their composition and texture, Curiosity helped confirm that ancient Mars had long-lasting lakes and rivers, rather than only short, violent floods. From time to time, the rover climbed low, rocky slopes, testing its wheels and systems as it worked its way toward the foothills of Mount Sharp. Eventually, Curiosity arrived at the western edge of a field of dark sand dunes known as the Bagnold Dunes, and then continued south toward a low ridge called Vera Rubin Ridge. While crossing this ridge, the rover's instruments recorded a change in the composition of the rocks beneath its wheels. The earlier terrain contained much silica and ordinary basaltic material. On the ridge, however, the rocks were rich in hematite, an iron oxide that commonly forms in the presence of liquid water. The fact that much of the ridge is made of this material is strong evidence that, in the past, the climate in this part of Gale Crater was significantly more humid. Water, either in the form of a standing lake or groundwater circulating through the rocks, must have interacted with the minerals over extended periods. Over the course of its mission, Curiosity has remained on Mars for more than 3,000 Martian days, or sols, which is roughly 5 times longer than the original mission plan. Despite dust, mechanical wear, and the challenges of operating in a cold, thin atmosphere, the rover has traveled nearly 30 kilometers across rugged terrain. Along the way, it has drilled into rocks and collected 28 samples for chemical and mineral analysis. These studies have detected not only water in various forms, but also organic molecules, including compounds such as benzene and other aromatic hydrocarbons. In this context, organic means that the molecules contain carbon and hydrogen. It does not by itself prove that they came from living organisms. Still, their presence shows that the basic building blocks needed by life as we know it were present in ancient Martian environments. At the same time, Curiosity's cameras have returned thousands of images and many panoramic views, helping scientists reconstruct the detailed history of climate and water in Gale Crater. Leaving this persistent rover behind in its long climb up Mount Sharp, we shift our focus to another major feature on Mars, far to the south and east, Hellas Planitia. This is one of the largest impact basins on the planet. It is thought that about 4 billion years ago, a massive asteroid with a radius of around 50 kilometers struck Mars here at very high speed. The collision released an enormous amount of energy, blasting out a huge cavity about 2,300 kilometers across. Millions of tons of rock were shattered and thrown outward, some landing far from the impact site. A portion of this debris may even have been launched completely off the planet, later falling back to the surface hundreds or thousands of kilometers away, or escaping into space as Martian meteorites. At the time of the impact, Mars was probably a more hospitable world than it is today, with a thicker atmosphere and abundant surface water. The deep lowland created at the Hellas impact site would naturally have collected water flowing from higher ground. Over time, it likely filled to form a great lake or an inland sea without an outlet to the ocean. Over billions of years, as the climate cooled and the atmosphere thinned, this body of water gradually shrank and eventually vanished, leaving behind the large basin we see now. Today, Hellas Planitia is a huge depression more than 7 kilometers deep in places relative to the surrounding highlands. When viewed from orbit, the floor of the Hellas Basin can look smooth and uniform at first glance. However, this impression is misleading. Closer examination reveals that the surface is broken into many small hills, ridges, fractures, and patterned ground. These features are thought to be related to the movement and deformation of subsurface ice. In other words, layers of frozen water mixed with dust and rock lie beneath parts of the basin floor. As this ground ice slowly shifts, melts locally, or refreezes, it causes the overlying soil to crack and buckle in characteristic patterns. On Earth, similar relief appears in Arctic and subarctic regions, as well as in other permafrost zones, where freeze-thaw cycles sculpt the landscape into hummocks, polygons, and small troughs. Because Hellas Planitia lies so far below the average level of the Martian surface, the air above it is denser than in most other places on the planet. Atmospheric pressure at the basin floor can be about twice the global average. This increased pressure, combined with its depth and local topography, gives Hellas some distinctive weather. From time to time, a misty haze forms over parts of the basin. Wisps of fog and low clouds drift across the lowland, a phenomenon that is relatively rare elsewhere on Mars. Winds carry some of this mist up the basin walls and out of the crater, but as the air rises into regions of lower pressure, the droplets and ice crystals quickly disperse or settle onto the cold rocks. During the Martian winter, temperatures in Hellas Planitia drop low enough for widespread frost and seasonal ice to accumulate. The basin becomes covered with bright patches of frozen carbon dioxide and water ice. Seen through telescopes from Earth, this brightening makes Hellas appear as a large, pale spot. For a long time, before precise altitude measurements were available, astronomers thought that this bright region might be a high plateau or an upland area reflecting more sunlight. Only in the late 20th century, when orbiters began to map the topography of Mars with laser altimeters and other instruments, did it become clear that Hellas Planitia is in fact a deep basin, not a raised land. Its true nature as one of the lowest points on Mars, with a unique combination of pressure, ice, and weather, was finally recognized. Our path now returns to Jezero Crater, this time with a closer look at what the rover and helicopter have been doing there. In the distant past, Jezero was the site of a large lake fed by at least two main rivers. One river flowed in from the north, another from the west. Even today, the remains of these ancient channels are visible on the Martian surface. They appear as sinuous valleys and as layered deposits of fine sediment that fan out where the rivers once met the lake. On the walls of the surrounding hills, we can still see broad scars and terraces formed as water cut into the rock and left material behind. This fossil river delta is one of the key reasons Jezero Crater was chosen as the landing site for the Perseverance rover. Lake sediments and delta deposits are excellent places to search for signs of past habitability and preserved organic matter. Perseverance descended into Jezero Crater on February 18th, 2021. The original plan was for the rover to touch down near a location known as Three Forks, close to the valley carved by the Western River. However, conditions during the final stage of the descent caused the landing point to shift by about 1.7 kilometers to the southeast. Between the rover's actual landing site and its primary target lay a region of loose, treacherous sand called Seita. The soft, rippled terrain there posed a significant risk to a heavy rover with 6 wheels and a strict energy budget. Driving straight across it would have been too dangerous. This is where the small Ingenuity helicopter, carried to Mars under Perseverance's belly, became particularly useful. Ingenuity flew above the surface and took wide-angle images of the ancient delta from the air, mapping dunes, rocks, and possible paths forward in detail that would be hard to obtain from the ground alone. On one of its flights, it also captured a unique view of a feature called Kodiak, a small plateau located about 2.3 kilometers from the rover's landing site. The layered sides of Kodiak are thought to be a remnant of the old delta structure, and aerial images help scientists interpret how water once flowed and deposited sediment there. Once Perseverance had completed its initial checks and surveys near the landing area, it began a careful journey westward and southward, skirting the edge of the sandy region rather than crossing it directly. Moving along the boundary of Seita, the rover stopped at intervals to drill and collect samples of rock and soil. Each core sample was placed in a sealed tube and stored on board for a possible future mission to pick up and return to Earth. Meanwhile, Ingenuity carried out flight after flight, scouting ahead and sending back images from perspectives that no previous Mars mission had achieved. The helicopter's views helped mission planners choose routes that avoided hidden hazards and identified rock layers of special interest. On Martian Day, or Sol, 168 of the mission, the team instructed Perseverance to turn westward. The idea was to drive along the crater floor, pass around the southern tip of the sandy area, and then reach a rocky ridge that could guide the rover northward toward the heart of the delta. However, as the rover advanced, it encountered rough terrain that would have been difficult and risky to cross. Large rocks, steep slopes, and patches of soft ground forced the team to reconsider. To avoid becoming stuck or damaging the rover, they commanded it to turn back, almost retracing its path towards safer ground near the original landing area. After this adjustment, Perseverance set out again toward its goal, this time following a route that stayed close to the northern edge of the sandy region. The rover gradually turned west, then northwest, taking a more cautious but safer path. At last, after a long and demanding journey over the crater floor, Perseverance reached the base of the ancient delta and began systematically studying it. This milestone was achieved in April 2022, about 413 Martian days after landing. Since then, Perseverance has traveled more than 18 kilometers across the Martian surface. It has drilled and stored 15 rock and soil samples and has sent back more than 166,000 images, along with gigabytes of measurements from its scientific instruments. Among those instruments is MOXIE, a small device designed to test a crucial idea for future human missions. MOXIE takes in carbon dioxide from the Martian atmosphere and uses electricity to split the gas into oxygen and carbon monoxide. Over the course of its operations, it has produced on the order of 100 grams of oxygen. In practical terms, this is a small amount, but it demonstrates that it is possible to generate breathable oxygen and rocket oxidizer from local resources on Mars, rather than carrying it all from Earth. Perseverance also carries a seismometer that has recorded several Marsquakes. These small quakes provide information about how seismic waves move through the interior of the planet, helping scientists refine their models of Mars's internal structure. At the same time, the Ingenuity helicopter has continued to contribute. It has completed more than 50 flights, covering a total distance of over 8 kilometers. Each flight proves again that aircraft can operate in the thin Martian atmosphere, opening a new way of exploring rough terrain and scouting targets for rovers and, someday, astronauts. In addition to the desert landscapes and rock outcrops along its path, Perseverance occasionally points its instruments at the Martian sky. In some of its images, a small white point can be seen moving slowly above the horizon. This is Phobos, the larger and closer of Mars's 2 natural satellites. In one notable series of observations, the rover recorded Phobos passing in front of the Sun, a brief solar eclipse on Mars. This event was not only visually striking, but also scientifically important. By measuring exactly how the sunlight dimmed and how the silhouette of Phobos moved, astronomers can refine their knowledge of the moon's orbit and internal structure. Mars has 2 moons, Phobos and Deimos, and both are small, irregularly shaped bodies. Observations and spectral studies indicate that their compositions resemble those of carbon-rich or carbonaceous asteroids. However, their exact origins are still debated. One hypothesis is that they are pieces of a small body captured by Mars from the main asteroid belt billions of years ago. In this scenario, tidal forces from Mars may have torn the original object into multiple fragments, with Phobos and Deimos being the largest survivors. Another hypothesis proposes that a large protoplanet collided with young Mars early in the history of the solar system. Debris from that impact could have gone into orbit around Mars, and over time, gravity may have gathered some of the fragments into 2 small moons. Phobos is the larger of the pair. It orbits Mars above the equator at an altitude of about 6,000 kilometers. Said out loud, that is about 6,000 kilometers above the surface, which is about 64 times closer than the average distance between Earth and its moon. In fact, some artificial satellites orbiting Earth, such as those in high geostationary orbits, travel 3 to 5 times farther from Earth than Phobos is from Mars. Yet Phobos is so small that, when seen from the Martian surface, it appears only about 1/3 the apparent size that the moon has in our sky, even at its closest. Its low mass and size also give it an unusually low average density, about 1.9 grams per cubic centimeter. This suggests that up to roughly 40% of its volume could be empty space. One possible explanation is that Phobos is not a single solid rock, but a loosely bound collection of blocks and rubble held together by gravity, a so-called rubble pile structure. Tidal forces between Mars and Phobos are gradually changing the moon's orbit. The interaction of gravity and the slight flexing of the bodies causes Phobos to slowly spiral inward, Current estimates indicate that Phobos is losing altitude at a rate of about 1.8 meters per century. Over long timescales, this adds up. In roughly 10 to 11 million years, Phobos may approach Mars closely enough that it breaks apart under the stress. Once that happens, the fragments would form a temporary ring around the planet. Calculations suggest that after another few tens of millions of years, those fragments would gradually fall out of orbit and rain down onto the Martian surface. By that time, Mars will likely have lost its second moon, Deimos, as well. At present, Deimos orbits Mars on a nearly circular path with a radius of about 235,000 kilometers. This distance is slowly increasing as tidal interactions transfer energy from the planet's rotation to the moon's orbit. In a few million years, Deimos is expected to drift far enough away that it will no longer be gravitationally bound to Mars and will move independently around the sunday. Deimos is a very dark object. Its surface absorbs almost 93% of the sunlight that hits it. Because it is also small, its disk cannot be resolved by the naked eye from the Martian surface. Instead, it appears as a bright point of light, similar in size to a star but moving in a predictable path across the sky. To an observer standing on Mars, Deimos seems to drift slowly in the Martian sky, and at times, its motion appears to carry it toward the path of Phobos. This apparent convergence is only an optical effect. In reality, both moons travel around Mars in the same direction, following their own orbits at different distances and speeds. Their steady motion, along with the shadows they sometimes cast on the planet below, continues to provide both beautiful views and valuable data for scientists studying the dynamics and history of the Martian system. In the final part of our journey, we turn to the main asteroid belt, one of the most dynamic and intriguing regions in the solar system. This broad ring of material orbits the Sun between Mars and Jupiter. So far, astronomers have identified and cataloged more than 300,000 small bodies here, each with its own name or numerical designation. The true number of objects, including smaller fragments, is probably well above 1 million. The modern study of this region is often dated back to the year 1801, when observers who had been searching for a fifth planet between Mars and Jupiter noticed a new star-like point of light. Its motion showed that it was orbiting the Sun, but even the best telescopes of the time could not resolve its disk. It looked like a star, and yet moved like a planet. This object was named Ceres. Soon, more similar objects were found, and a new term was introduced for this class: asteroids, literally star-like bodies. In addition to the larger asteroids, the belt contains vast amounts of fine dust. These tiny particles slowly spiral inward under the influence of sunlight and gravity. As they do, they scatter sunlight and create a faint whitish glow along the plane of the solar system. This glow is called zodiacal light. Under very dark skies near Earth's equator, it can be seen with the naked eye as a soft, wedge-shaped column of light stretching up from the horizon just before dawn or after dusk. For a long time, a popular idea was that the objects in the main belt were the remains of a single planet that had somehow been destroyed. Today, that simple picture no longer fits the evidence. One problem is the total mass of all the known bodies in the belt. When we add them up, we get a value of about 3 times 10 to the power of 21 kilograms. Said out loud, that is 3 times 10 to the power of 21 kilograms, only about 4% of the mass of Earth's moon. Even if we assume that many asteroids were lost from the belt over time, the amount of material still seems far too small to have once formed a planet of normal size. The second issue is the strong gravitational influence of Jupiter. Detailed computer models show that in the region of the main belt, the pull of the giant planet constantly disturbs the orbits of growing bodies. Whenever developing protoplanets became large, their orbits were driven into unstable patterns. Instead of combining into a single world, many of these objects would have collided and broken apart, producing the debris we see today. The signatures of those collisions are still visible. Many asteroids are grouped into families, that is, clusters of bodies that share similar orbits and compositions. These families are thought to be the fragments of once larger parent objects that were shattered by violent impacts. The borders of the main belt are fuzzy, but most of its mass lies between about 2.06 and 3.27 astronomical units from the Sunday. Within this region, there are special zones known as Kirkwood gaps. These are distances where the orbital period of an asteroid would fall into a simple resonance with Jupiter's period, for example at a ratio of 3:1 or 5:2. In such resonances, the repeated tugs from Jupiter clear out bodies over time, making their orbits unstable. As a result, relatively few asteroids are found in these gaps compared with neighboring regions. One of the most important gaps lies at about 2.5 astronomical units from the Sunday. This resonance marks a convenient boundary between the inner and outer main belt. In the outer part of the belt, near its middle, we find its largest member, Ceres. Ceres was first called a planet, then reclassified as an asteroid, and in 2006, it was given a new status, dwarf planet. It qualifies because, unlike most asteroids with irregular shapes, Ceres is massive enough for its gravity to have pulled it into a nearly spherical form. Its diameter is about 940 kilometers. Its mass is about 9.4 times 10 to the power of 20 kilograms, which is roughly 1/3 of the total mass of the entire belt. Even so, Ceres is about 6,000 times less massive than Earth. Ceres follows an orbit that carries it from about 2.5 astronomical units at perihelion to about 2.9 astronomical units at aphelion. Near its closest approach to the Sun, the surface temperature may rise to around 239 Kelvin, which is about 34 degrees Celsius below zero. On average, its surface is much colder, with temperatures near 167 Kelvin, or about 106 degrees Celsius below zero. Models of its interior suggest that Ceres has a rocky core wrapped in a thick shell of frozen material, a cryomantle about 100 kilometers thick. Water ice may account for as much as half the dwarf planet's volume, and perhaps 20 to 30% of its mass. The presence of this ice, along with some salts and possible signs of past briny flows, makes Ceres an important object for studying water-rich bodies in the early solar system. In the inner part of the belt lies Vesta, the largest and most massive object that is still classified as an asteroid rather than a dwarf planet. Vesta has an average diameter of about 525 kilometers and a mass of about 2.6 times 10 to the power of 20 kilograms, almost 4 times less than the mass of Ceres. Its orbit is somewhat elongated, with a perihelion distance of about 2.15 astronomical units and an aphelion of about 2.57 astronomical units. It takes Vesta about 3.6 Earth years to complete one orbit around the Sunday. Vesta is unusual among asteroids because it can sometimes be seen from Earth without a telescope under dark skies. Its visibility is due not only to its size, but also to its relatively bright surface, which reflects about 42% of the sunlight that falls on it. The minimum distance between Vesta and Earth is about 177 million kilometers, or about 1.18 astronomical units. Vesta appears to be a differentiated body, meaning that it has separated into layers in a way similar to a small planet. Evidence suggests that it has a metallic core made mainly of iron and nickel, surrounded by a rocky mantle. Today, the surface temperature on Vesta varies roughly between about minus 190 degrees Celsius and about minus 20 degrees Celsius. But in the distant past, it must have been much hotter. Dark plains on its western hemisphere are likely volcanic in origin, formed either by ancient lava flows or by material melted in large impacts. The most striking feature on Vesta is a huge impact basin called Rhea Silvia near its south pole. Rhea Silvia is about 500 kilometers across and up to about 25,000 meters deep. At its center rises a mountain more than 22 kilometers high, one of the tallest known peaks in the solar system. The size of the crater, almost matching that of Vesta itself, suggests that the asteroid once collided with a very large object. That collision is thought to have produced not only Rhea Silvia, but also a great number of fragments that now make up the Vesta family of asteroids. This family includes more than 15,000 known objects, about 5% of all cataloged members of the main belt. Not all large asteroids are compact, solid worlds. Some are rubble piles, loose collections of rocks and voids held together mainly by gravity. A good example is Silvia, one of the larger bodies in the belt. Silvia has approximate dimensions of 384 by 262 by 232 kilometers and a mass of about 1.5 times 10 to the power of 19 kilograms. Its average density is only about 20% higher than that of liquid water, suggesting that empty cavities make up perhaps 25 to 60% of its volume. Silvia takes about 6.5 years to complete one orbit around the Sun, traveling between about 3.2 astronomical units at perihelion and about 3.7 astronomical units at aphelion. Some of the debris left over from a past collision that formed Silvia did not merge back into the main body, but instead became small moons. Silvia is known to have at least two companions, Romulus, with a diameter of about 18 kilometers, and Remus, about 7 kilometers across. Their compositions are still not well measured, but it is likely that they, too, are not fully solid inside. It is also possible that Silvia has smaller satellites that have not yet been detected. Another major asteroid is Pallas, discovered in 1802, shortly after Ceres. Pallas is the second largest asteroid in the belt by size, with an average diameter of about 512 kilometers. Its mass is about 2 times 10 to the power of 20 kilograms, roughly 25% less than the mass of Vesta. Pallas has an orbit that is both elongated and strongly tilted with respect to the plane of the solar system. Its orbital plane is inclined by about 35 degrees, which makes it challenging to reach with spacecraft that usually travel close to the ecliptic. Pallas takes about 4.6 years to go around the Sun, during which its distance from the Sun varies from about 2.1 astronomical units at perihelion to about 3.4 astronomical units at aphelion. Its surface is heavily cratered, even more so than those of Ceres or Vesta. Studies of its spectrum show that it is composed mainly of silicate rocks with some iron and water-bearing minerals mixed in. Like Vesta, Pallas is often considered a leftover protoplanet, a building block that never grew into a full-sized planet. Most asteroids, however, are far smaller and cannot be seen without strong telescopes. One of the more enigmatic large objects is Interamnia. This asteroid has an irregular shape with dimensions of about 362 by 348 by 310 kilometers. Its mass is estimated to account for about 1.2% of the total mass of all objects in the main belt. Yet Interamnia remains poorly understood. One reason is its very dark surface, which absorbs about 93% of the light that falls on it. It belongs to a rare spectral class known as F-type, a subgroup of carbonaceous asteroids. Its overall color appears fairly uniform, which implies that it has not suffered a major disruptive impact for a long time. The bulk density of Interamnia is only about twice that of water, suggesting a structure with a solid rocky core surrounded by a thick shell of ice, all covered by a layer of fine, dark dust. It takes Interamnia about 5 years and 4 months to complete an orbit, traveling between about 2.5 and 3.5 astronomical units from the Sunday. In theory, its path crosses the orbital ranges of Ceres and Pallas, but calculations show that the chances of an actual collision are very small. Although there are millions of bodies in the main asteroid belt, from dwarf planets down to small meteoroids the size of cobblestones, the distances between them are enormous. Typical separations are measured in hundreds of thousands or even millions of kilometers. A spacecraft passing through the belt faces only a very small risk of accidentally hitting an asteroid. Even so, over long timescales, collisions do happen. Models suggest that, on average, a major collision that creates a new family of fragments may occur roughly once every 10 million years. These events reshape the population of the belt and send some fragments into new orbits that may eventually cross paths with planets. Several asteroids in the main belt have already been studied up close by interplanetary probes. The Dawn mission, for example, visited both Vesta and Ceres between 2011 and 2016, mapping their surfaces and measuring their compositions and gravity fields. More recently, the Lucy spacecraft was launched to explore the so-called Jupiter Trojan asteroids, but on its way, it will also fly past a small main belt object named Donald Johanson in 2025, taking images and collecting data. Another mission, Psyche, is aimed at the largest known metallic asteroid in the belt, also called Psyche. Launched in the middle of this decade, the spacecraft is planned to arrive at its target around 2026 and remain there for at least about 21 months. During that time, it will study the asteroid's surface, interior structure, and magnetic properties, offering a rare look at what may be the exposed core of a former protoplanet. The solar system, although it is the most thoroughly explored part of space, still holds many puzzles in regions like the main asteroid belt. Beyond it, the Milky Way stretches outward, containing billions of stars and perhaps trillions of planets. As we continue to send instruments and someday people into space, there will be many more discoveries waiting in the depths of our galaxy.